Have you ever dropped or thrown a rock into a pond and watched the ripples go out? I'm sure you have. Guess what? That's what we're going to talk about. Earthquakes. Wait. That's a rock in the water. Yeah, but you're causing a vibration, and it goes out in ripples or waves from that point of vibration. Well, we've discussed that the rocks are moving against each other. They're solid as opposed to liquid water, but you have the same ripple effect going out. It's not just that even. You know, that we should have a ripple effect in our Christian life. We should be talking to others about the Lord, and they can then talk to others, and it just spreads out. So it's not just even earthquakes and water waves, but other things that can have a ripple effect. Now, we're going to talk about a couple terms that can get mixed up that have to do with the location of the earthquake. First, if you look at this, the focus is the starting point of the earthquake. Now, it can be near the surface or it can be very deep, but it is underground, caused by the rocks sliding. Now, the point that we tend to focus on that's important to us, because we don't live under the ground, is the other term, and that is the epicenter. Can you see how that's directly above the focus, but it's at the surface? In other words, that's where the maximum earthquake vibration is on the surface, because it's the closest. You know, if you're over here, that's further away. So go straight up, no matter how deep that the focus is, go straight up from it and you come to the epicenter. Okay. How do we measure earthquakes? With what devices? You probably know this. There's a seismograph that measures the amount of movement of the earth. It detects the back and forth motions of the earth. Now, those have been around, I don't know exact dates, but 100-ish years, something like that, with maybe in a manual device that has no electronics in it. It could be even longer than that. I do know that if we go back to the period right after the last book of the Bible, the New Testament, was written, we have this, Chang Hing's dragon jar. And you can see there are little spouts coming out of different parts of the jar, and then there are cups underneath them. And so as the earth would vibrate, whichever direction it was vibrating in, then the water would tend to slosh out, and those two, and they could see by which of the cups had water and how much water there was, a general idea of direction and intensity of the earthquake. We'll talk about the intensity later on. But how do scientists determine where the epicenter is? Well, they use a method called triangulation. You see there are 3 dots. That's where 3 seismographs are taking readings. And they can measure the direction by the distance. See how we have all 3 of them intersecting right there at the middle. That's the epicenter. Okay, so it's so far. Now, that happened to be exactly the same distance from each of those points. It doesn't usually work that way, but just for simplicity on the drawing. You go this far from that seismograph, and that seismograph, and that one, and there's the epicenter. Okay, so we're measuring and putting those together, those 3, to find out exactly within maybe a mile or so where the earthquake is centered and located underneath the focus, but where that epicenter is. This is done in other things. I've read some books about World War II. For example, in France, the resistance would have hidden clandestine radio sets that they would go into a building and they would, Morse code over to England. The Germans had listening posts and they would triangulate and find out where within maybe part of a block or so, depending on exactly how well it was set up, where that's coming from. And sometimes they would have trucks with detectors would drive around and be able to pinpoint it even closer and then send a squad out to try to get those resistance people and arrest them and destroy their transmitter. So that's another example. Same way with radio waves. All these are vibrations that we're triangulating on and finding the source. You'll be doing that if you look at your activity manual on page 3 and 4. There is an expansion where you do just that if you choose to do it. Now, what we need to do is talk about the types of earthquake waves. First of all, let me emphasize to you that there are two main categories: body waves and surface waves. Okay, so we have all the earthquake waves and they break up into two main categories, body and surface. Each of those categories is going to have two specific types of waves. So make sure you understand the framework before we start filling it in. Okay? Body and surface with two types. So there are really 4 types of waves. 2 in the body, 2 in the surface category. So let's start out by looking at body waves. They occur beneath the Earth's surface. That's why they're not surface waves. They're in the body of the Earth. And the 2 types of body waves are P and S waves. We'll look at each one of those individually. P waves, simple, push, pull, P, push, pull. Like we had the SSS for the type of fault. We have P, push, and pull. That'll help you remember it. These, you can see them pushing together and pulling apart. These move faster than any other wave type. They travel in straight paths, and they can move through both solid and liquid material. So they can go right through the liquid areas inside the Earth. Okay, that's like the mantle. The S waves, they're moving in up and down zigzag pattern. And obviously I said the P waves were the fastest, so these are going to be slower. And they do not travel through liquid. So they are going to go through the crust and the outer solid portion of the Earth, not on the surface, but down deep in the solid area. They won't go into the mantle. Okay, so remember, we have the 2 types, body and surface. So we've got the body waves and the surface waves. Okay, and the body waves were P and S. Okay, now we're going to look at the 2 types of surface waves. They are at the Earth's surface, and they are slow moving in comparison to both the P and the S. P is faster than the S, but the S is faster than the surface waves. They are very destructive. And the 2 types of surface waves are Love and Rayleigh. Okay, so let's look at each one of those. Love waves move slowly back and forth. Okay, and in comparison, we have Rayleigh waves, which move in a rolling motion. I don't want to say up and down, but it on the surface of the Earth, that's what happens as they're rolling around, is that it's going like this as opposed to sideways back and forth. Okay, so these surface waves are the ones that cause the damage to our buildings because they're on the surface. How do we measure the amount of earthquake that has just occurred? Well, we have a scale to measure it. Just like you have a bathroom scale to weigh yourself, we have a scale to measure. There's actually two of them. The Mercalli scale is used in cities and areas where there's a lot of buildings by measuring destruction. So we observe the city, the town, afterwards. You know, you look, this building has this damage and that damage, this damage. And so the Mercalli scale is applied afterwards by looking at the damage. Okay? The other scale, and this is the one you probably heard, it's the more commonly known, the Richter scale. It measures the magnitude or the size of the earthquake, the largeness. That's what that Latin word magna means, large, the largeness of the earthquake. Now, when you probably heard about earthquakes and their Richter scale numbers. Maybe, oh, this earthquake is a 3.5. This one's a 4.9. This one's a strong one. It was 6.1. And those numbers, they don't seem to mean anything. Okay, so I need to explain how the Richter scale works so that you can get a concept of it. The main thing to understand is that it is not a normal number scale. What I mean by that is, on a normal number scale, if you have one object and you have a second object, you have twice as much. If you put a third object on, you have, 3 times as much, of course. But that's not the way the Richter scale works. It's not that normal number scale. There's a special term for it that you'll learn later on. But each change of one number is 10 times more. So when you go from 1 to 2, you're not doubling. It's 10 times stronger. When you go from 2 to 3, it's again 10 times stronger, and 3 to 4, and 4 to 5. Each one of those is 10 times stronger. Now, what do we do with all those 10s? We multiply them. Don't add them. We're multiplying them. In other words, when you go from a Richter scale earthquake of 1 to 2, it's 10 times stronger. 10 times more energy, intensity. From 2 to 3 is 10 times. So from 1 to 3 is 100 times more. Let's look at a couple examples of that. How much greater is a magnitude 4, we're talking about Richter scale earthquake, than a magnitude 3? What's the answer? 10 times. How about a 4 than a 2? 10 and 10, 20. No, remember what I said. What do? You multiply them. So it is 100 times. Now, how about this one? How about an 8? How many times greater is that than a 3? So go from 3, 4, 5, 6, 7, 8, and see what you come up with. Did you get 100,000? Yep. That's what it is. From 3 to 4 is 10, 4 to 5 is 100, and so on up to 100,000. Now, what does this look like then, the damage that's done? Well, here's a little diagram, picture, illustration that shows you if you have a Richter scale magnitude of 2, you're asleep, you're not even going to feel it. With 3, some things vibrating. Remember I talked to you about the chair and feeling it vibrating? So I think that was somewhere right around the 3. Then a 4, you can have things falling. Okay, 5, there's structural damage like the glass breaking on windows. With 6, you have damage to houses and there's cracks in the earth. When you get up to around the 7, it's causing lots of destruction. And 8, it basically, that's like the San Francisco when you get up to 8 and even in the 9. The largest I have written down was a 9.2 that I was able to ascertain. I know in 1964 in Alaska, they had a very long, in duration of time, earthquake. It was about 3 minutes. And it was also a very intense one. The water in the harbor went completely out and came back in a huge wave. Now, those harbor waves, the word for that you might have heard is tsunami. That's a wall of water that can be 10, 20, 30, whatever feet high, that moves in at many miles an hour and just goes inland and mile after mile after mile. I believe it was in Japan not too long ago that they had an earthquake underwater that made the water come in and have a tsunami, have a harbor wave, and many people were killed. You've probably seen videos of that. So we've looked at the different types of waves and talked about how we measure them and make sure that all of this is understandable to you, that you've got a hold of it before you go on to the next lesson.